This lesson is about plane electromagnetic waves and particularly the problem of normal incidence between two materials. So we speak of this problem as a scattering problem in which we define the reflection and the transmission of these waves in the passage from one material to the other. This is our general framework in which we have material 1, material 2. The two are characterized by mu naught, mu1, epsilon 1, mu2, epsilon 2, the constitutive parameters of the two materials, by two different wave numbers and by two different wave impedances, eta 1 and eta 2. The general solution when a wave is incident on this material from material 1 to material 2, the general solution in terms of waves is that of an incident wave, a reflected wave, and a transmitted wave, as shown in this picture. What we want to find is the coefficients that characterize these reflected and transmitted waves from a known incident wave. In particular, we have that in medium 1, we can write the electric field as the sum of the wave that travels along the positive z direction plus a wave that travels in the negative z direction. These two waves have a given wave function, e exponential minus j k1z, which is the positive wave, and a minus exponential j k1z, which is the negative wave, whereas in medium 2, the electric field has a single wave that is the transmitted wave that is characterized by coefficient b plus exponential minus j k2z. So we can write, in addition, in material 1 and in material 2, in addition to the electric field, also magnetic field. And if we write the corresponding components of the magnetic field for a given electric field, we observe that the magnetic field is related to the electric field by the wave admittance, 1 over the wave impedance, eta 1, and by this minus sign for the minus wave, because the second wave, the reflected wave that is produced by the interface, has a change in the direction of magnetic field, when we assume that there is no change in the direction of the electric field. So it's the relative sign that is important. The two parameters, square root of mu1 and epsilon 1 and square root of mu2, epsilon 2, are the two different wave impedances. So that the reflected wave is produced because we cannot match the tangential electric field and tangential magnetic field because of the fact, for a single wave, because of the fact that the wave impedance is different. As you see, in medium 2, there is a single wave. Let's not forget that an electromagnetic wave is the combination of two fields, electric and magnetic field, that travel together. But there is a single, as you see, coefficient that is associated to each wave. So that in material 2, there is a single coefficient B plus that is associated to the amplitude of the wave, and then there are two fields, E and H. Similarly, in material 1, there are two waves and two coefficients, one per wave. First coefficient is A plus, the incident wave. Second coefficient is A minus, the reflected wave. So what happens at the interface? We have the conservation of the tangential component of the E field and of the H field. So we substitute, the interface is set at z equals 0, we substitute z equals 0 here, and we obtain a relationship, two relationship between the coefficients. Of course, everything is proportional. We rewrite these two equations here, but everything is proportional to the input, to the amplitude of the incident wave, so that we can divide by the amplitude of the incident wave and obtain two relationships between two coefficients. First coefficient is the ratio between A minus and A plus. Second coefficient is the ratio between B plus and A plus. These two have a name. The first one is the reflection coefficient, ratio between the amplitude, complex amplitude, of the reflected wave and the incident wave. Second coefficient is the transmission coefficient, which is the ratio between the amplitude, complex amplitude of the transmitted wave divided by the amplitude of the incident wave. Therefore, the two equations that represent the continuity of the electric field and the continuity of magnetic field can be written as 1 plus gamma equals T, continuity of electric field, 1 minus gamma over eta 1 equals T over eta 2, which is the continuity of magnetic field. two equations with two unknowns, we can solve for gamma and t. And the solution is shown here. Gamma is eta 2 minus eta 1 divided by the sum. And t is 2 eta 2 divided by the sum. So we can, using this expression, we can also find a value for eta 2 from the knowledge of gamma and eta 1. And is simply obtained by simple substitution from these expressions. And we find that this is the expression. Of course, when the two impedances of the two materials are the same, the reflection coefficient is 0, which means that the reflected wave is not produced, but the transmission coefficient is non-zero, so there is a transmitted wave. So we see that the reflected wave is produced as a result of the difference in impedance. We can also state what is called the power conservation or the power density conservation, because we are in the presence of materials that do not absorb. But anyway, at the interface, there is a flux of power density that is associated to the incident wave. There is a flux of power density associated to the reflected wave. And there's a flux of power density associated to the transmitted wave. Of course, since there is no power dissipation anywhere in this problem, the total power reflected plus transmitted must equal, the total power density must equal the incident power density. So we can write that P1 plus, the power density associated to the incident wave, must equal the sum of the other two. And since we can express the power density as a function of the field variables, we can also write this power conservation at the interface in terms of the two known reflection and transmission coefficient. The difference is that now there is also the appearance of the change in these two numbers. These two numbers, G1 and G2, for instance, G1 is the real part of the inverse of the wave impedance. So it's the real part of the wave admittance. If the material is lossless, as in this case, this real part corresponds to 1 over eta 1 simply, because eta 1 is real. And so is eta 2. So that this can be seen as the equation of power conservation that states that for a given input power of value 1 that is incident from material 1, the power reflected, which is the power density associated to the reflected wave, is the square of the magnitude of the reflection coefficient. And the power transmitted to material 2 is the square of the amplitude of the transmission coefficient multiplied by the coefficient G2 over G1. Now, in the lossless case, eta 1 and eta 2 are real, so that the expression becomes very simple, and we can observe that the reflection coefficient is always a real number that is limited between a minimum value that is -1 and the maximum value that is 1. The transmission coefficient, for similar reasons, is real and is limited between a minimum value that is 0 and the maximum value that is 2. In the lossy case, in which, for instance, material 2 has some dissipation effect that can be due to imperfect dielectrics, so real dielectrics, non-ideal, or conductive, so real conductors with finite conductivity, we have that the wave impedance is complex, as shown in this picture. So that associated to the reflected wave and the transmitted wave, in particular the transmitted wave, there is also an attenuation. So that what happens in material 2 when material 2 is lossy, has some losses, we have simply an attenuation of the transmitted wave that in its propagation in material 2 loses amplitude because of absorption of material 2 itself. There are two special cases that we can point out. One is the case of good dielectrics. Good dielectrics are characterized by a loss tangent that is much smaller than 1. And for these, we can assume that the wave impedance is still real, so we can neglect in the expression of the wave impedance the small loss tangent. So that since eta 2 can be considered to be real, also gamma and t are still real. The expressions are shown here again. But in the propagation of material 2, due to losses, we also have an attenuation. This attenuation can be expressed as a function of the parameters of the material by this formula. So that in material 2 we have, if the material 2 is very long in extension, we can not neglect the absorption, and we must include the attenuation. The second special case is that of good conductors, in which the impedance is the well-known impedance of good conductors, which is 1 plus j times the square root of omega mu over 2 sigma. Mu, of course, is the mu, the permeability of material 2. In this case, since this is a very small number, because good conductors have a very high value of conductivity, this is a very small number, as we can neglect its presence, almost neglect its presence, in most cases, in the expression of the reflection coefficient, that is very close to -1. And the transmission coefficient also is very close to 0. This means that these are not exactly -1 and 0, but for a quick estimate, we can consider them to be -1 and 0. For this case of good conductor, we also know that we have a closed form expression for the propagation constant in the conductor, and the attenuation constant is the conductor as a function of the material parameters.